Okay, so this is spring 15, number 11. Somebody wanted me to do one like that. Oh yeah, so you're definitely going to have some questions like this where I ask you to tell me what is the net magnetic field, and that's sort of what this is doing, where you're finding the magnetic field due to two or more wires, and then tell me what is the net magnetic field. So in this case, I have two wires that are down. I do my right-hand rule. This is the one where my thumb is in the direction of the current. So my current is down, so my fingers go into the page on this side. So due to this wire, it's into the page. And then on the other wire, due to this wire, the magnetic field is out of the page. So here at point A, I'm going to have one magnetic field that is out of the page, one magnetic field that is into the page. So those are going to cancel out and give me a magnetic field all along this center line that is 0. So there's no magnetic field at that point. So if I had two wires, let's say that I had this one was going in that direction, well, then it would be a little bit different because I would have a magnetic field that would be out of the page due to that wire, and a magnetic field that would be out of the page due to that wire. So then at point A, I'd have one that'd be out of the page, another that would be out of the page, so C would be the right answer. Yeah, it would still be 0 if they were both up. It's just, you know, they would be opposite, yeah, but they would still add up equal to 0. So I'm pretty sure you have one like that, and then I definitely remember that you have one where you have multiple wires, say, kind of like we did today, where you say you have a wire like that, and a wire like that, and maybe a wire like that, and I ask, what is the magnetic field over here at point P? Where I'll give you a series of vectors, and you have to pick out which is the correct vector. So the way that you do this, let's imagine this one is out of the page. Well, what is the direction of the magnetic field at point P? Let my thumb come out. It wraps around in a counterclockwise fashion. So imagine I get a big circle. I'll draw it, but then I'm going to take it away. Up at point P, I get a magnetic field that's in that direction. Okay? So I'm going to draw that vector then like that. That's due to the wire that's coming out of the page. Due to this wire, I'm going to get a magnetic field that's in that direction. And then due to this wire right here, that one's into the page, so it's going to be in that direction. That's not obvious what the sum of those three vectors are. If you give one, when you have one like this, it will be fairly obvious because, I don't know, it'll be a vector like maybe 2 like this and 1 like this or something along those lines, okay? But that would be the first step, is to find the 3 or more vectors and then take the sum of those vectors. Let me see what these messages are. It might be somebody. Oh, no, that's something else. Okay? Y'all can do that, right? Yes. Okay. Let's go with a free response. Just make sure that we're all up to date on that. Let's see. Yeah, so this is number 1. This is spring 21. I think that spring 20 didn't have a free response. That was that crazy year. Yeah, 19 has one, and it has a similar one. Let's do this one. I think we've actually done the 21, so let's do this one. This one is similar. Definitely, you're going to have, like part A, at what time is the charge on the capacitor 5 microfarads? Just realize first, this is a charging capacitor. And so when I look on my equation sheet, I get that Q is equal to Q times 1 minus e to the minus t over RC. It doesn't have to be that. I mean, it can be one of the other equations too, but you would solve it in much the same way, okay? And then remember that big Q is equal to C times V, which in this case, that would be 3 times 6, or 18 microcoulombs. So I'd have equal to 18 minus 18 times e to the minus t divided by RC. This is R, this is C, so t divided by 6. And then I would solve this. This is going to be equal to 5. I would solve this for t. The way I'd do that, let's see, 5 minus 18, so that's minus 13 divided by negative 18. Is equal to e to the minus t divided by 6. So I would take the natural log of both sides. The natural log gets rid of this, so that t over 6 comes down comes out of that exponent. And then the natural log of 13 over 18. Make sure that you can do this in your calculator. There's a natural log 13 divided by 18. I get negative 0.33 equals negative t over 6, and then I get t equals, what, 1.9 seconds. Okay? So that's how you do that. I just want to make sure that you know how to handle algebraically the exponential function, because it's an important function for all sorts of fields in the life and physical sciences. And then also, what is the time constant? Remember, this is a characteristic time. This isn't how long it takes to charge or discharge. We've already found the time constant, actually. It was equal to 6 seconds. That was equal to R times C. And then if I want to know the time to fully charge, that's going to be 10 tau. So that's going to be 60 seconds. And then sketch a graph. Well, this is a growth function. So if it's following this type of function, that's a growth. It's going to look like this. If it's the e to the minus t, that would look like that function. That's a decay function. Okay. Let's see. I don't remember. I might have had a multiple choice or something about percentages. I don't remember if I did or not. We've seen those before. Let's just do that. Let's say I asked, what is the percentage at t equal 4 seconds? What percentage is the current? What is the percent of the current equal to at t equal 4 seconds? Do y'all understand what I'm asking? I've had similar questions to this on previous tests. Y'all follow what I'm asking? Okay, let me just show you. So I would ask, what percentage of the current is there at t equal 4 seconds? And so current is always this, whether it's charging or discharging. This is from your equation sheet. E to the minus t over RC. And if I wanted to know the percentage, by the way, this is just my maximum current, right? I is equal to V naught over R, so that's my maximum current. In this case, that would be, let's see, V is 6, R is 3. No, R is not 3, R is 2. So that's 3 microamps. The reason it's microamps, by the way, because it was 6 volts divided by 2 mega ohms. Okay, so I have a 10 to the 6 in the denominator. Don't be thrown off by that. We haven't really seen that before. But anyway, so I'd have, at 4 seconds, the percentage is I over I naught, and then that would be e to the minus t over RC. Like, this would be the percentage, right? If my max is 2 and I have 1, then that would be 1/2. And so the percentage then would be e to the minus 4, that's the time, divided by the time constant, which we said was 6. And so that would be e to the minus 0.67. Make sure you know how to do that. A second natural log e to the minus 4 over 6. And I get 0.51. So that's equal to 51%. Let's look at the equation sheet. I think y'all might be a little bit confused about that. So if you look at the equation sheet, if ever I ask you a percentage, the percentage is always given by the growth of the decay function. That e to the minus or the 1 minus e to the minus. So if ever I ask you for a percentage, then you're simply just calculating that. So if I ask you for what is the percentage of the voltage at a particular time, then you're calculating this. Or if I ask you what is the percentage of the charge for a discharging capacitor at a particular time, then you're calculating that. Because the percentage, for example, would be Q divided by Q, right? So I would just have e to the minus t over RC. Or it would be V divided by V naught, which would be equal to that. So if I wanted to know the percentage of the voltage right here, I would just say e to the minus t over RC. Or I would say the percentage is 1 minus e to the minus t over RC, depending on, you know, am I looking at a charging or discharging or charge, voltage, or current? I see very non-committal looks on your faces. Follow that? I'm pretty sure there's a question like that on the exam. There aren't that many examples, but there are a few. Okay, yeah, so that is on the equation sheet. That's why I wrote it like that, right here. See this equation for our current of a charging or discharging capacitor? But it comes from Ohm's law, right? V is equal to IR, so I is equal to V over R. We do V naught, that's just the way of saying that's the voltage of the battery. That's what that means. No, it doesn't have any effect on the percentage calculations. You would still, the percentage would still be this. Because I could rewrite this equation. That's getting messy, sorry. But I could rewrite this equation, and it would just be I equals I naught times e to the minus t over RC. Sorry, my pen is messed up. You follow? Yeah. You follow? If ever I ask you the percentage, I'm looking for the exponential. Either 1 minus e to the minus t over RC, or just e to the minus t over RC.
How do you know whether it's charged?
Oh, good question. So I will tell you, let's look at some exams. And so how do I know if it's charging or discharging? Okay, so here on number 1, for example, I know that this is charging, although in this case it doesn't really matter because I'm just asking the time constant. I know it's charging because it has a battery in it. When it has a battery, it'll always be charging. You won't have a discharging capacitor with a battery in it. So that is the first clue. Otherwise, I mean, I would say this capacitor is discharging or this capacitor is charging. I think, in fact, I usually say that. Like right here in number 1, I say how long does it take to completely charge the capacitor, and then how long does it take to reach that charge. So it's accumulating charge on that capacitor. Let's see a good example of a discharging capacitor. I know that this one is charging, again, because it has a battery in it. And so the answer here would be current. Excuse me. This is current. I'm looking for current over time, so the answer here would be this, A. I could know that because if I look at the equation sheet, I'll find that I is equal to I naught e to the minus t over RC. For either charging or discharging capacitors, the current. And so this function right here is always this graph. That's the decay function. And the current always starts out big and then declines, whether you're charging or discharging the capacitor. Yep. And again, look at your equation sheet. So there's a lot of different equations for this. But notice here, this says charging or discharging for current. And so this little thing right here will clue you in that it'll look like that your graph will look like that. But if it's charging, then you know it looks like that. Or if it has this 1 minus e, this one would look like that. This one would look like that. So it matters, is it charging or discharging? And are we looking for voltage, charge, or current? Okay? So really, I just want you to be able to identify the exponential. Is that a growth or a decay? If it's 1 minus, it's decay. Excuse me. If it's 1 minus, that's growth. If it's e to the minus t over rc, then that's the decay function. Okay? Let's go back to our free response. Which one were we doing? This one. So you'll have something like this. Then you'll have something like number 3 right here. Number 3 is a mass spectrometer, because I have this charge entering into a magnetic field and it has a certain radius. So there are a couple equations that you'll need to, well, you don't need to know them, but it's probably better if you know them. The cyclotron equation, which is right here, this R equals mv over qb. That's the cyclotron equation, but really I think it's better to think about this qvb, which is our magnetic force, is equal to my centripetal force, mv squared over r. That the magnetic force is equal to the centripetal force, or it is the centripetal force. And ultimately, that's where we get this equation, that we just solve that equation for r, and we get mv over q v. Okay? Well, let's go back to that test. Here, if I want to know the radius of the path that the proton follows, well, I would say R equals mv over qb. It is a proton, so you know the mass and the charge, and now you know the magnetic field, and you know the velocity or the speed of that particle, so you can calculate the radius. And then also, there will probably be an application of the right-hand rule in this question. I have a positive charge that's traveling with a velocity in this direction, and it has a force in this direction. That is the magnetic force. Excuse me. I can calculate, I can determine the direction of the magnetic field. It's going to look like this. So the magnetic field is out of the page. So it's going into a magnetic field that is out of the page. That means our magnetic field is here. Okay? And that causes it to go down in that direction. As I told you in class, that if I give you, which I will, it'll be a little bit different than this. I'll give you the speed and the radius and the magnetic field, and ask you to calculate the centripetal force. The centripetal force is mv squared over r. Or I might give you qv and b, and you need to recognize that the magnetic force, which is qvb, that these are the same. These two quantities are the same. Right, you understand that, right? That the centripetal force is the magnetic force. Or rather, it's really more correct to say that the magnetic force, which is a physical force, that it is the centripetal force. It is that force that causes this object to move in a circular path. So you will have to calculate the centripetal force in that free response. Okay? You're going to have a little right-hand rule going on. Probably have to calculate the mass to charge ratio like we've been doing in class. So what was that? That was capacitors. What was the third question that we have? What did I tell y'all? Oh, it was like the wire. So one, like this one, number 4, where you have to calculate the magnitude and direction of the magnetic field at the location of the electron. So what is the magnetic field? Well, B, let's go back to our equation sheet. I always forget. So the magnetic field due to a long straight wire is mu naught I over 2 pi r, excuse me. Mu naught I over 2 pi r. I can tell this equation is really similar, but remember, because this has the N value, that's for the solenoid, or the loop of wire, the coil of wire. So for the long straight wire, I'm looking at this. Mu naught is given right there below it.
Fix the question now. Specify like the long straight wire, or like is it gonna say like straight wire or something so we know the difference?
I think I drew a picture like this. Like this is straight, right? Yeah. I think so. It doesn't look like a loop to me. Yeah, I think I used a very similar figure to this. But yeah, if I don't, I will say loop or straight wire. Yeah. So I'd say mu naught I over 2 pi r. I have I, it's 2 amps. So this is 4 pi times 10 to the minus 7. Minus 7? Yeah. 2 divided by 2 pi. It's convenient. And then the radius is 0.25. So the pi's cancel, the 2 cancels, gives me that 2. So I get 4, I get 16 times 10 to the minus 7. So that is my magnetic field. You'll have to calculate that magnetic field and then calculate the direction and magnitude of the force. So now that I know this charge is moving through this magnetic field, I can calculate the force that it feels. This is an electron, so it's 1.6 times 10 to the minus 19. The speed of it is 3 times 10 to the 5th. And now I have the magnetic field, which is 16 times 10 to the minus 7. And then you calculate that force, and it is whatever it is. Okay? Just beware, because students usually mess this up, is that if you have a proton or an electron, you know the mass and you know the charge of those. So that's a lot of information packed into that one word, that I know its mass and they both have the same charge, which is the fundamental unit of charge, that 1.6 times 10 to the minus 19. Okay? All right, that's the free response. So that's 8 questions. That's a quarter of the exam. What other things do y'all want to look at? Yeah, shoot. Oh, yeah. I'm pretty sure you're going to see that. Let's... Yeah, because we don't have chapter 6 in this exam, I just have more opportunity to ask questions, so I'm pretty sure that made it. What? Look, see here it says straight wire, number 11. I don't remember who asked that. Okay. What am I looking for? Oh yeah, electric field. I can't find one. I'll just make one up. I used to do these freebie questions at the end of the exam, like who's your favorite student, or yeah, it's because y'all don't have as many questions, so I can't just throw them away.
You could just add an extra one that's worth 10 points if you look at
That's really funny. Oh shoot, I don't see any. No, that would mess up my whole grading scheme. What is that?
Okay, I have a question while you're on that page. The last question on that page before, that question was on the quiz.
Number 8?
Yes. Can you like explain?
Yeah.
Like, would you just like...
Mm-hmm. So this is just like the one that we did before.
Right.
Or I didn't really do one, but this is a great example of finding those percentages. That's what this is asking. Good question. What? Leave her alone.
Well, it didn't have any numbers in it. I remembered it on the quiz, and I remember practicing it.
Yeah, there are numbers. There's a number right there. 3.
Oh.
That's the only number you need. So first of all, am I charging or discharging this capacitor? That's initially uncharged. is charging, and I'm looking for the voltage. If I look at my equation sheet, voltage for a charging capacitor looks like this, right? So V is equal to V naught times 1 minus e to the minus t over RC. I'm looking for what is V over V naught. Whenever I say percentage, that's what I'm looking for. The ratio of V to V naught. This is V at a certain time t. This is the maximum V. And so it's going to be 1 minus e to the minus t, or excuse me, 3 tau over tau. Because I'm looking for what is the percentage when t is equal to 3 time constants. This is 1 time constant, so I just replace that with tau, and then replace t with 3 tau. So those cancel away, and the answer is just 1 minus e to the minus 3, whatever that is. Okay? Well, let's see. 1 minus... I get 0.95, so the answer is 95%. Okay? Great example of the type of question that you would have. But I'm still looking for... What is it that I'm looking for? What was it? Oh yeah, the magnetic electric field. Yeah, so like number 5. Hold on, let me just look at something right quick. It's been a while since I wrote this exam, so I don't remember. Let's get that out of my phone. Electron and a magnetic field, the GFCI, the wire. Where is it? Oh, there it is. Okay, so I'm not going to give you all the details, but let me just show you in short. Say if I have a charge that is moving in this direction. It has a certain speed, it's moving through a magnetic field that's like that. The force that it feels will be, let's see, up, right? It feels an upward force. So FB is upward. What if I also had another thing that was causing a force? Let's say that I had a magnet or an electric field that was going in this direction, or whatever. If this is a positive particle, then that force, or that particle, will feel a force that's in which direction? Left, right, up, down? To the right, right. Positive particles always feel the force in the same direction as the electric field. So the force, the electric force on this particle would be in that direction. Okay? If it were negative, it would be opposite. You want me to tell you what I'm going to ask? I'm going to ask you, what is the net force on that particle? Do you know how to find, if you find those two forces, how do you find the net force? On basic vector stuff? Or do the what? The what? Like, let's say that FB is equal to 2 and this is equal to 3, how would I find the net force? Right, I'd say the square root of 2 squared plus 3 squared. And then that would be the answer. Okay? The direction of what? Oh, well, you don't, so you have two independent forces. You have the magnetic force, which we find, and then you have the electric force. And the electric force is in the, if it's positive, it will always be in the same direction as the electric field. Yeah, I'll give you the electric field. Yeah. Do you know how to find Fe? It is. Ooh, I don't know if I put it on your test. Oh man, I didn't. I'll give it to y'all before the class starts. So if I want to find F, this is what I'm doing, right? F is equal to Q times E. We've done that. Y'all have done that a bunch. Y'all remember? That was chapter 2. Okay? It's kind of important because we use electric and magnetic fields a lot together to manipulate particles. All right. Can y'all remind me to give you that equation on the board? F equals QE. I don't like doing that, but I forgot to put it on there. All right. Is that helpful? You understand what I'm talking about here? That you'll have to figure out what FB is. FB is QVB. And then also you have to figure out the direction of FB. And then you have to figure out what FE is, and that's QE. And then also you have to figure out the direction of QE. And then determine the net vector. Pretty sure they were perpendicular. I don't remember. If they're the same direction, you just add them. If they're opposite directions, you just subtract them. I don't remember what the directions of them were, but it would be one of those three options. Either they're perpendicular, where you have to do this. They're in the same direction, where you just add them together, or they're opposite directions, where you just subtract them. Okay? Are we clear on that? Y'all get that question? There's just one question like that. This number 5 is a similar question where you're setting QE equal to QVB. And you're looking for V. So V then is equal to E divided by B. So that these two cancel out. Well, let's see. So the electric force would be in this direction. Because it's an electron, it feels an electric force that's opposite the electric field, and the electric field is down. The velocity is, which way is it going? Well, so yeah, it doesn't tell me the direction. I want the magnetic force to be down because I want to cancel the magnetic force. I want them both to cancel out. And so in order to have a velocity that gives me a force that's down, well, my thumb is in this direction. It would have to be like this. So you'll see how I'm doing that right-hand rule. My thumb is in the direction of the force. This is in the direction of the magnetic field. And now this finger comes out of the page. So then if I was asking for the direction of the velocity vector, it would be into the page because it's a negative particle. Okay? I didn't ask that question here, but it's not an irrelevant question because, you know, applying the right-hand rule in that way. All right. What other questions, John? particular things, don't forget to review your household circuits. There'll be questions like these. I don't know, 3 or 4 questions about household circuits, 3 or 4 questions about RC circuits, and then 4 to 5 questions about each. No, I'm sorry. I think there were like 6 to 7 questions about chapter 4, and then 12 to 14 questions about chapter 5. No freebies. No freebies. That one, I just gave you this question. Yeah. So if you want to know the magnetic field of a wire, then you let your thumb go in the direction of the wire, and then your fingers wrap around. So that's just the magnetic field of a wire. But if I have some charge with some velocity vector, so if I have a velocity vector, then that's where you're using this one. Current due to, or magnetic field due to a wire. If I have a velocity vector, then I'm using this one. But sometimes they're combined, right? What's that? Right. So if I'm looking for, oh, that confuses you, doesn't it? So if I have a force on a wire, then that's this right-hand rule. So I guess maybe force is the better way to think of it.
Current and you're looking for the field,
use the thumb.
Anything else, use this.
Yeah, but also don't forget that on your free response, you're going to have both. All right, so this one right here, you had to do both for this question. Because first I had to figure out the direction of the magnetic field due to this wire. That was the thumb, right? So it's into the page, out of the page, over here. And now I have a charge moving in a magnetic field that's out of the page. So that's where I use this right-hand rule, not the thumb, but the orthogonal one. Where now, let's see, so force would be down, except it's a negative particle, so it's up, right? Okay?
So we use the thumb.
Yeah, you have to use the right-hand rule for the thumb, right, to find the magnetic field, and then the right-hand rule to find the force.
Yeah, so it's the wraparound, and then it's the...
Yeah. But y'all might be a little bit confused because if I have a wire in a magnetic field like this, and I ask what is the force, well, this is where you'd use this. Okay, so just because it's a wire doesn't mean it's the thumb. That it might be this. If you're asking for the force, then you have to use this, because then you have 3 orthogonal vectors. So here my force would be none. Okay? Not an easy test. Because a lot of students struggle with thinking of it as 3-dimensional vectors, and we have some things coming back, like electric fields, and even that centripetal force. But y'all can calculate this force, right? 50 squared over r. Remember that. It's not going to be a surprising test, but not an easy test. Somebody said it was the hardest test. I don't know who that was. I think they were joking. But it's not the hardest test, I don't think.
What's the hardest test? Don't say the last one.
The first one. Don't you think that was hard? Really? Okay. Anything else, y'all, for today? I'll be around tomorrow. I'm in class much of the day, but I am around some. So if you have questions, let me know.